I'm going to talk to you about rotor sail propulsion technology. Now, isn't it amazing, 100 years on, and here we are, we're going back to wind power. Quite remarkable, really. So just when you thought there was no new technology, well, it existed all the time, we moved away with it, and now we're going back. Jukka has an MSc in Naval Architecture and Marine Engineering and an MBA from Helsinki University of Technology. He worked with ABB Marine Business Unit for 15 years in management positions on special projects, sales and marketing and service operations. Before joining Norsepower in 2016, Jukka worked in the wind power industry with wind turbine manufacturer, and also with Element Power, a wind power project developer. Jukka is responsible for sales and marketing at Norsepower. We had a little conversation over lunch, and I asked him whether or not this is exclusively for ships, or if we're going to start seeing multi-million-pound super yachts floating around with wind blades on them. And he said that potentially that's yes. So it was exciting. Jukka, the floor is yours for you to speak. Thank you very much.
Thank you, Mike. Good afternoon, and thank you for the opportunity to speak about rotor sails, auxiliary wind propulsion. Norsepower is a company established in 2012 with a task of bringing sailing back into merchant shipping. Sailing has been, this is my history slide, has been, of course, integral part of shipping for maybe thousands of years. But of course, the last 100, 150 years, we've seen steam engines, diesel engines, the sort of typical propulsion systems of today be the mainstream. But we've seen in the past years the potential for reducing fuel consumption on ships which are using fossil fuels for propulsion to be a big benefit, because with fuel consumption, we save. Saving fuel consumption saves money, it saves emissions, and that's all good for us. So I'll talk about how Norsepower developed the old Flettner rotor invention into a modern mechanical sail, and how we plan to go forward with it. So we were established in 2012 with the sole target of modernizing the Flettner rotor technology to become applicable and suitable for modern merchant shipping. And our first rotor sail was installed already in 2014 on the Rotor vessel you see on the slide. It's the Estraden, owned by Pure, a Finnish company, today owned by Splithoff, which is a Dutch ship owner. And this ship is sailing between Rotterdam and Eastport on the UK side, so across the North Sea on a regular weekly schedule. So we have soon 3 years of I'll show some slides later on to highlight that. And this has nothing to do with Norsepower, but it's okay if you just maybe I'll try to speak and that's not mine. The rotor sail is based on a physical phenomenon called the Magnus effect. There is a video which I plan to show, which wasn't that one, which is about highlighting how the Magnus effect works, because it's something we're all familiar with from ball games such as tennis or football, where you put a spin on a ball and the ball has a curved flight path instead of straight. And the reason why the curve happens is the Magnus effect and the force that is pushing the ship, in this case the ball, to a curved flight path. So to highlight that the rotor sail is a sail providing thrust for the ship to reduce the propulsion power required on the main propulsion. So we're not generating electricity from wind, we're using wind as a sail. And this is an auxiliary wind propulsion system that is applicable for different types of ships. The main requirement is that there is space on the deck for installing the rotor sail units. Then we need some electrical power, roughly 50 to 100 kilowatts per unit to rotate it. And it's all, of course, dependent on the wind conditions where the ship sails, how much potential for savings there are. So whenever the wind conditions are good, such as North Atlantic, the Southern Oceans, North Sea, there's very good potential for savings. If the ship sails predominantly in the equator area, for example, the wind conditions are lower, there will be savings, but less so. Here's a video where a basketball is dropped from a very high dam, first without a spin. And you notice that what happens is quite expected. The ball drops almost straight down. There is clearly some wind down there to drive the ball a little bit sideways. And now with a good spin, we see how the ball flies in a different manner. Goes all the way to the lake, bouncing off. So that highlights what happens in the Magnus effect. So the red ball on the left has the spin. It causes a small amount of air to spin on the surface of the ball. And as it's accelerated, there is wind meeting against the ball, causing a pressure difference on both sides of the ball, because on the other side the flow is accelerated, on the other side it's decelerated. So accelerated flow means reduced pressure, and this pressure difference is one of the main reasons for this Magnus effect. And we can imagine that the rotor sail, the rotor cylinder, it's a stretched ball surface. So as we make it rotate with the electrical drive, it causes this same thrust force through the Magnus effect. As mentioned in the beginning, this is an old invention, so this is not an innovation that Norsepower or anyone recently has done. Mr. Anton Flettner from Germany, and same time Mr. Sigurd Savonius in Finland worked on these concepts and developed and proved that this works. So we modernized this concept. And how to highlight the operation in a schematic here. We have an actual wind direction and speed. Then as the vessel has a certain speed, it creates the speed wind in addition. So the rotor sails, they see a relative wind coming. And then our automation system decides which rotation direction should be used to make sure that the force is forward. So it's helping the main propulsion. And this Magnus effect creates the lift force at a 90-degree angle from the relative wind. Also, it creates a drag force, as we can expect. And the automation system is dividing these forces into components and has the task of maximizing the thrust so that we can save as much fuel as possible. Of course, the other components of the force are sideways, so they are trying to deviate the ship from its course, and they are counteracted by the rudder and the surface of the side of the hull, so which is acting like a keel. On the first vessel, the Ro-Ro vessel, the captain and the crew have said that there is no correction that they need to do for directional stability, because also that would be a disadvantage for resistance and fuel consumption if they had to correct it with the rudder constantly to counter the sideways forces. So this is also good news for us, that the forces are not that big that they would cause additional steering requirements. Here a whole diagram which shows how the lift force is generated depending on the direction of wind and the speed of wind. So here at the zero angle from top down, we have the wind direction from the bow, and from bottom up is the wind direction from aft. And with the curves which are showing the magnitude of the thrust, or in this diagram we've transformed it into kilowatts, equivalent kilowatts on the propeller. We see that as the wind speed increases, the different colors are different wind speeds, up to 25 meters. The equivalent power is increased, and the most beneficial wind direction in this case is about 120 degrees. So slightly from the aft, and this is due to the ship speed being 17 knots, which means that the 90-degree angle, which is the perfect angle for the true wind, then is relative wind 130 in this, 120 in this case. So from both sides of the ship, as the wind blows, that is the most beneficial direction. And if there is direct headwind, it's the same as any sailing ship, you would have to start tacking to be able to do that, but this is not what we suggest for merchant ships. We just slow down the rotor sail to reduce the drag force, and the ship would hold its normal course, of course. So how is this constructed? We have the outer surface of the cylinder. It's a composite carbon fiber, glass fiber construction, a sandwich construction, which is as light as possible, but also very strong and rigid. And this is one of the key issues for modern technology, to be making this technically possible, to make a light rotating large cylinder. It's supported by the steel support tower, which is this gray one, and that's the stationary part, which has then an upper support bearing and an electrical drive up here to rotate the cylinder. The lower support or rollers, they mainly take care of the radial position. Obviously, when rotating up to 250 RPM, this kind of a large rotor has to be very well balanced. And this is one of the modern manufacturing technology, and of course the balancing technology makes this possible. Installation and interface for the ship is a steel block foundation, which is welded on the ship's deck. And then we have cables which are drawn from the main switchboard and the automation unit to the rotor sail unit for controlling it. Weight of the units which we've seen on the Estraden is about 25 tons, and the largest unit which will be installed on a Magnus tanker during next year will be about 50 tons with the foundation. So that's the range of weight that we have for these designs. Average electrical consumption of the electrical drive is between 50 and 30 kilowatts, roughly, depending on operation, which means that that's how much we are expecting to use on an average. And any benefit that we claim for fuel saving is, of course, the net benefit. So we are then subtracting that out of the gross savings. Shipping routes, of course, which you are very familiar with, are going through the main hubs. And the most beneficial areas then, when we look at the wind conditions, the average wind speeds, the red colors being the higher wind speed areas, and yellow and blue. Blue is mostly on land, but the yellow colors are then the lower wind speeds. We see that ships sailing mainly in the red areas, they are very potential for good savings. And if a ship goes more in the yellow areas, then we can expect that there is less potential for savings. But anyhow, savings are possible. So the components in a delivery are control panel on the bridge and DCR, wind and anemometer. In this picture, we have a ultrasonic wind sensor, the steel foundation block, and then the actual rotor sail, which is installed as one piece with a crane, either mobile crane from the land side, or as in this case in Rotterdam, the first ones were installed by a crane barge during the port call of the ship. So the preparation works, cabling and foundation installation, they were done during dry docking, and the actual lifting and installation of the rotor sail was done during 7 hours for the first installation and 5 hours for the second. So they were well within the port call time, not requiring any off-hire from that operation. Here is some drone footage from the ship visiting in port. The rotor sails are now rotating slightly faster than you would expect in idle mode, just to have them visual here on the video. And the main point that the crew has made, why they think these are also from their perspective good and appreciated, are that they don't create additional work. It's something they don't need to deal with. There is a button for start on when they leave port, but they don't even need to switch it off when they come to port. It's automatically switching off when ship speed is reduced below 8 knots. So here we see they are rotating at the nominal 250 RPM, and this size, the 18-meter high unit in very high wind speeds, would create roughly 1 megawatt of propulsion power equivalent. So 2 of them would support the main propulsion by up to 2 megawatts. The average being, of course, less than that in this condition, or this route, it's closer to 400 kilowatts. I mentioned about how the testing was done for proving that there is real saving from the propulsion power and therefore also fuel consumption. As we know, the wind is different every day. The environmental factors are so complex that it's impossible to sail one day with rotor sails and come back the other way without and then start to determine something. So what we did was a 10-month measuring campaign, switching the rotor sails on and off 70 minutes each. So every 70 minutes it was on and every 70 minutes off. And with NAPA supplied equipment, the 2 power curves were able to be drawn with the measurement data. So a regression analysis was done after with those thousands of measurement points to determine what is the power curve without rotor sails and what is it different, how is it different when rotor sails are in operation. And that's when a reliable result was achieved, say 6.1%, which was the result for that. And for this ship, it meant 2 tons per day less fuel consumed. So the experience summarized, thrust performance is as expected. So physics works as we thought it would. Yes, please.
I'm just wondering the performance, positioning the sails in line one another against putting them side by side.
Okay, you mean the physical location?
Yes.
Yes, okay. So on this ship, both were the most convenient locations, not interfering with cargo space, and there was some strengthening required for the deck ramp house to withstand the loads. The main point is to have sufficient distance between the rotor sails so that they won't interfere with each other and have shading effects or turbulence effects. Same thing for the superstructure or funnels, for example, that they're not too close. The recommended distance is 10 times the diameter of the rotor. So for this model, 30 meters minimum distance would be sufficient to maintain the efficiency. Whether they're side by side or one after the other doesn't really matter. There is some effect on how to place multiple rotor sails with reference to the center of rotation of the vessel, if we think of the directional stability, but otherwise no difference, as long as they are well exposed to wind. Mechanical construction has been very well proven. Availability is high. Noise and vibrations are at a low level, so even on passenger vessels, this would not cause noise issues or vibration issues for the passengers. And the automation works as intended. So it's easy to use. It's something that the crew will not consider as an additional work. Also, stabilizing effect was noticed. This was not one of the targets or benefits that was early on considered, but there are two reasons for that. One is the gyroscopic effect of a mass rotating around its vertical axis, and it's trying to resist the deviation from vertical. That's one point, and the other is the sail effect, just like on a sailboat, so that it's leaning from wind and stabilizing somewhat. And why the crew has paid attention to this is that the GM has been very high on this vessel, so it's been rather too stable for very rough movements in heavy seas. So they noticed that after rotor sails were installed, the motions were somewhat slower, accelerations reduced, so they were quite happy with that. However, it's been rather complicated to try and measure the quantity of this reduction of rolling, but anyhow it's noticed. And the financial reasons are also proven. Fuel consumption is reduced, and the monetary savings coming from that. Of course, the cheaper the fuel, the longer the payback period, but the other way around as well. As fuel might increase in price, then this kind of a system becomes a quicker investment to pay back. The projects that are upcoming is Viking Grace, cruise ferry that is sailing between Finland and Sweden, Turku and Stockholm. This will be a retrofit installation during the first half of next year. So there's going to be one 24-meter high unit installed on the top deck. Then Maersk, which I mentioned, will install also one on an existing vessel during next year. Or we'll install 2 units actually. And this is the largest model, 30 meters high, 5 meters in diameter. And the expectations are of saving up to 10% of annual fuel consumption on their operating profile. And while we estimate that up to 20% average fuel savings are possible on this type of a ship, we see that 4 units are also possible to install. So if it was done that way, then it would be up to 20% instead of 10%. And the new building project, where we still have the negotiations ongoing, but because the equipment is specified in the contract, we can show it here. Viking has ordered the ship from Xiamen shipyard in China, the first new building of such type from a Chinese shipyard, so a very interesting project. And that is specified with 2 rotor sail units, the same size as Viking Grace, so 24 meters. Also, air draft is an important question for some ship types, and of course always on route dependent. So we've developed a tilting model, which has a hinge module between the rotor sail and the foundation, so that we can lower the units down to horizontal if needed for going under bridges or if there are other aircraft limitations. So we have a mission to reduce the environmental impact of shipping and providing the easy and efficient auxiliary wind propulsion systems. We are today the market leader. There are at this time no other suppliers that are at the same level of development and capability to deliver rotor sails, but we know there are companies developing this, and we look forward to having competition. We think that's an important part of market developing and gaining confidence for this new concept. So I hope that was informative, and if you have questions, I'll be happy to try and answer.
Memory serves me correctly, so there was a ship built in 1922-23.
Yes.
Well, with the Rotor ship. She lasted, I think, about 3 years before the others came up.
Yes.
2 questions I have. Do you know the reason why they got rid of the Barbara? And 2, have you considered the maintenance of that motor? How do you get inside to look at it?
Okay.
What are the costs of that?
Of course, yeah. How does the surveyor work? Yeah, exactly. Good questions. On the first one, as I've learned, the power consumption of the first units was too high. So it was sort of wasting energy that it was saving, and the difference wasn't big enough. Also, the technical challenges, the heavy rotor unit, which was part of the energy consumption challenge. Yes, there was aluminum and steel and other attempts. So that were the main reasons that it didn't pay off. Plus, diesels and fuel was so well available and proven at that time. And the other question about how to check and maintain, simple maintenance has been one of the key issues as well in our design. So we have twice per year maintenance cycle, which is rather simple checking and greasing of some rotating components. We can climb into the unit. The support tower is hollow, welded construction. I myself have climbed into all of the units that we have, so it's possible to do. You don't have to be a very small guy to be able to fit in. And we have its ladders up to the top for the electrical drive, and we can inspect and maintain all of the equipment from the inside. So it's not a problem.
Thank you.
So. Okay.
He had 6.1% saving with 2 rotors.
Right.
Probably doesn't necessarily follow. You can have 4, but that's double the saving.
Yes. So it's basically when they are. Yeah, you can multiply by the number of rotor sails as long as they are in equal locations, meaning that they are exposed to wind in a similar manner. Yes.